Loud. Okay. All right. Good night, everyone. Good evening, everyone. Thank you for joining us for another of our Belmont Talk series. This is a monthly quasi TED Talk series, sharing some of the expertise of people who are in and around the Belmont community, who have knowledge and expertise in various topics that they have kindly offered to share with the Belmont community. These presentations are the brainchild of the Belmont Parks and Recreation Department's volunteer coordinator, Susan Rendina. So thank you, Susan, for your ideas and energy to make this a successful program. And thank you to the Belmont Library for sharing their technology and their space for us to offer this program in person and on Zoom. And for the Belmont community, we are recording these programs. They're available through the Belmont Parks and Rec website, through the volunteer page. And so you can see the series of talks we've had since January of this year. If anybody in the community has some expertise that they would like to share, please feel free to reach out to us and let us know. We're always looking for new topics that are of interest to the community. And so without further ado, tonight's talk is all about the sun. And so I'm proud to introduce Professor Mohsen Janatpour. He's a professor of math, physics, and astronomy at the College of San Mateo. He's also the coordinator of the CSM astronomy program and has been sharing his wisdom at CSM and beyond for 43 years. And we are very pleased to have him here this evening. So without further ado, Professor, I'm going to hand off to you. Thank you so much.
Thank you so much. Thank you for a nice introduction. Thank you. Thank you. So I'm going to start by actually this image. And the reason I have that particular image, originally, I think Susan had approached a colleague of mine, Daryl Stanford. And Daryl asked me to do this. And I said, well, provided you give me the images. I had a lot of cool images. Some of the images actually come from my friend here, Ken. And it's hard to pick good images. One thing I like about this, these are the first 4 images I show were taken by Daryl at our own observatory. Before I start, I want to give you a kind of pitch for the event that is coming up. On September 24th of this month, CSM will celebrate Family Science Week, which I run again. On that one, I run the program with the help from my friends like Ken. And in that event, which starts at noon on Saturday, 24th, and continues all the way to about 11 p.m. We have a fantastic show, great cast of scientists and lecturers that are enjoyable. The theme of our Family Science Day is James Webb Telescope, which right now is the hottest thing that we know. Every image, every other day I get images that is unbelievable. How many of you have seen the image of the Jupiter that was sent? That was crazy image, okay? So based on that, we decided the theme of event is going to be there. And our speaker that night, our keynote speaker, which is at 7 o'clock in the evening in the theater, is Dr. Tom Green. He's one of the people who actually works with the James Webb team. And so you can ask great questions that is beyond my understanding. He can answer. So having said that, if you didn't get anything out of it today, make sure you come that day. Now, I want to talk a little bit about the sun, and I want to stay relatively general. So with the apologies or to experts, I'm going to try to give you something that when you get out of here, you look at the sun, you say, oh, is that the case? Pardon me? Oh, you can. When you look at the sun, whether you want it or not, you always look at the sun. No matter, you shouldn't stare at the sun. Big difference. Do not stare at the sun. But I mean, you cannot not look at the sun and put systems up. Also, you don't have to look at the sun directly. There are always all kinds of filters that you can look at. So now let's going back to the story here. This image was taken by Daryl, and I believe so was this one. So was this one, and so is this one. All three of those were taken by Daryl. The only difference between them is that different kind of filters that he put in front of his telescope. That brings me to another thing that I want to put a pitch for Ken. Ken is spent most of his life chasing eclipses and studying sun. And he is also giving a presentation at our talk. And the presentation, if he does, he brings his telescopes with a super cool filters, so you can look at his, through his telescope, look at the sun that day, 24th, assuming the sun is going to be up. Because sun has been up so long now, maybe he's going to take a rest and not show up for a while. All right. So now, first, let's start with some very basic. Okay. The first thing a lot of time people ask, and in fact, one of the first things that even in the antiquity people asking, how far away is the sun? How far it is. So that one is nowadays we can do easily. In fact, everybody can measure it nowadays. It is about 93 million miles. Now, that is not quite true. That's the average. See, if we don't go in the same circle around the sun, we go in an ellipse around the sun. So consequently, sometimes we're farther away, sometimes we're closer. When we are closest, which is called perihelion, near the sun, we are at about 91.5 million miles. And when we are far away, aphelion, which is on the other side, is about 94.5. So average of 93 is a pretty good number to remember. Now, I'll come back to that again, but think about it. The distance from here to the moon is only about 250,000 miles. This is 93 million miles. But that's not that far away. Incidentally, that's a great distance, because if it was much smaller, we would vaporize and there won't be any life. If it was farther away, we would freeze, and then again, we cannot survive either. That's sometimes people call that kind of distance the Goldilocks distance, because that's the time that life is possible. Now, the second thing is about the temperature of the sun. By the way, I have rounded these numbers the way I like to round for my students, because I don't want you to remember it is 9,840 or nonsense like that. 10,000 is a good number to remember. Okay, that's the surface temperature of the sun. By comparison, the temperature in your ovens, when you really turn it way up, it's around 500 degrees. So this is about, think about it, that's about 20 times hotter than your oven. Now, oops, I went too fast. Well, I can talk about it. But the temperature at the center of the sun gets really hot, because there's a lot of pressure, radiation pressure, and so on. So its temperature would be around 27 million degrees. And you need that for thermal nuclear reactions. That's how we get that. We'll come to that in a bit. But the next thing is, well, how much hot is the sun? If you get 330,000 Earths, put it on one scale, that would be about the mass of the sun. And in fact, here's the thing that a lot of people don't know. And it's the first time that I read it was mind-boggling to me. Of the mass of the solar system, all of it, include all the planets, asteroids, comets, and clouds, and all the dust, everything in the solar system. Mass of the sun is 99.84% of that. Okay? Only a small, about 0.16% of it is the mass of the rest of it. So you can see sun is extremely massive. And it wouldn't last as long as we want it to last. That's important, because sun constantly is converting mass to energy to give us the heat that we need. And next thing I want to say also that is the pressure. That one is mind-boggling. The pressure at the core of the sun is almost 4 trillion psi. 4 trillion psi. Now that is a number to say, but hard to imagine. Yes.
What is PSI?
I tell you that. That's a very good point. I'm going to tell you. Good question. The answer is pound per square inch. If you get a pound and put it on your hand and push, that push is 1 psi. Right now that you're sitting here, your skin is being pushed by atmosphere. It is at about 14.7.8 psi. Means that many pounds of pressure per square inch. Does that make sense? Okay. Now, the tires, the car, the pressure inside it is somewhere, when you go to it, somewhere around 30 to 50 psi. That one is about 4 trillion psi. That's very high pressure. Now, sun is mainly made out of hydrogen. And in fact, that is the fuel that is using constantly converting it into helium and giving us energy. It fuses the helium nuclei or the hydrogen nuclei together into helium. As a result, you get what we call radiation, the light that you get. Now, here comes about the size of the sun. It's kind of interesting too. Again, I am rounding the numbers because I like rounding up. So 87,000 miles, which is a number that I like. That is 870,000. About, here's what I want you to remember. If you get Earth, stack them up, one next to each other, go from one side of the sun to the other side, you need to put 110 of them next to each other to get the sun. Does that make sense? 1, 2, 3, keep put down next to each other. In other words, the diameter of the sun is about 110 times the diameter of Earth. Does that make sense? It is huge, huge, huge. Now things start getting bizarre. Okay, let me tell you. Come on, change it. Aha. Differential rotation. I want to tell you what that is. Have you ever seen toffee maker machines? How they make toffee? You've seen that it just turns and turns. The part that is in the middle turns at different rate that it is at the other side of it. You see that? That's a differential rotation. You see, Earth rotates 24 hours a day. And no matter where you are, if you're on the equator, it takes you 24 hours to go around. If you're in San Mateo, it takes you 24 hours to go around. That is not the case with the sun. The middle of the sun, this turns a lot different rate than the top of the sun. There's the big difference. I know it's different part of the sun as you go from equator to the north, they rotate at different rate. They don't rotate at the same rate. In fact, it goes from about 30 days a rotation all the way to about 25 days a rotation. And that has amazing consequences because you see, on Earth, when we rotate, the magnetic field of the Earth rotates with it, no problem. But on the sun, when it rotates, magnetic field lines get confused, they get tangled up. And that tangling up the magnetic field lines has amazing consequences, good and bad. And I will tell you a little bit about it. Now, this one is just telling you the sun is not a spectacular star, okay? It is a mediocre star, it's a G2 type V, okay? And it's not, if you look at the sequence, you're not a O star, we're not B star, we're, G star. And in the G star, we are not even G1, we're G2, okay? Which means we are the second bright one, okay? So, and That's okay, because that makes the life possible. So that's about that. Now, it is yellowish. Actually, the range of the color that sun sends us the most is about 550 nanometers. That's why our eyes are so much sensitive to that particular color. That's why you see a lot of the people who are making jackets to make sure people see it, they make it in those colors. So that's how we have evolved to see. And now, the light is produced at the sun and it has to come here. And it takes about 8.3 minutes to get here, okay? So if the sun was disappearing from the universe, you still have 8.3 minutes, okay? So that's not too bad. But it's easier said than done to understand. I want you to do that. I want you to say 1,000.
1,000.
Say it a little bit faster.
1,000.
That's 1 second, okay? In that 1 second, the time that she said 1,000, the light goes from here to New York and back here 30 times. It goes around the Earth 7 times, okay? And still it takes about 8.3 minutes to get from the sun to here. So that's a good thing to know. All right, now let's continue. I want to go a little bit talk about I like this schematic first because, oh, by the way, some of these images I have taken are from NASA's site. Thank you for help with that. Okay, some of the images are from NASA's site, and I picked up the ones that has the least amount of mathematics in it. Okay, and the reason, yes, for my wife. Okay, I wanted to make sure that we are not to worry about that. If you look at it, I'm going to go over here, put my finger on it, see that. You start with the core. This is what we do. Hello, how are you? We start with the core, okay? And then around, and I'll come to it about it. I just want you to see these numbers. You're around 86,000 miles or 87,000 miles around here in the middle. That I told you, 870,000. Jesus, like that. Okay, just take that as a part of the senility. All right, so as you move, the next zone that you have above it is actually radiation zone. And that is where a lot of light that is produced tries to travel. And here's the interesting clue to that. When the light is produced there, it doesn't just come right on top. It doesn't, because it does what we call, in physics, we call them random walk. When a photon is produced, it doesn't go straight up to the surface of the sun. So what does it do? It does a random. What's the random walk? Random walk is that they walk, it's like a drunk walking. They go one way, and then they go the other way, and they hit the thing. Sometimes they go to the back, and then they hit something else, hit the table, chairs, and all kinds of things. But eventually they get there. But it takes them a while. How long? The estimates are from about 170,000 years. So the light that you're getting today is at least 170,000 years ago produced. Okay? The estimates go actually up to 1 million years ago. So it takes a long time. When about 34 years ago, I was a visiting scholar at Stanford. She was my girlfriend at the time. And I was working with a guy, his name was Dr. Walker, he passed away since then. And the work we were doing was on sun. There was one thing that we were working on. That one thing was called neutrino problem. Because when the sun is producing energy, along with it, it produces neutrinos. And at that time, we are talking about 34 years ago, people were wondering what the heck is going on, because the amount of the neutrinos that we get on the surface from the sun didn't match the amount that physics said it should be produced. One of the things that they sometimes said, they were produced, but they were not sent out enough. Yes?
What is a neutrino?
neutrino is a subatomic particle. It's a particle, generally atoms are made of three kind of main ingredients: protons, electrons, and neutrons. Okay, but when you break them out, when you break a nucleus, it produces a lot of other subparticles. Okay, it's like if you get something, a ball, and you smash it against the wall, it breaks. And those pieces that come out, okay, one of those subparticles that comes out is called neutrino. They're very strange particles. We don't know exactly how it works. If you want to know one thing, right now you are sitting here, but you don't know it. Millions of neutrinos are going through your body, and you don't know that. But don't worry, it doesn't bother you. Okay? So it's going. For us, we are sitting in, for example, in Japan, you're sitting in big mines, okay? Miles and miles of rocks and water and everything else, trying to catch one neutrino. Okay, so it's a very tricky thing. Now, if you go to this picture, as we move up, you come to an area near the what we call mantle or the convection zone. That is where things start churning. I'll give you a better pictures in a minute. That's the time that the basically material in the sun is boiling. If you want to think about it, think about the way if you put water in a pot on top of the stove and let it boil. The way the water boils, actually, the hot water comes on top, okay, and it cools down, it goes down, gets warmed up again, come back up. That process is called convection. And that's how the convection ovens work, the same thing. And that is exactly what happens to the sun. And that's the region that we call that convection, right? Okay, so we have the convection zone right above that, and that is actually the part of the sun that most observers can see, is that we call photosphere. That's the layer that you see, and you can see that one is only about 250 miles deep. It's not that much compared to the rest of the sun. And above that is a layer that we call chromosphere. And then things get bizarre, really bizarre. And that's one of the things that we've never seen before. And we have some idea of the solution. There are two good solutions proposed, but nobody knows what the answer is yet. And I recently read that if you want to exactly find out what's going to happen, you need to set up an experiment that will cost about $800 billion to do. I don't think anybody's going to do it unless Ken can afford it. Okay. Now I'm going to show you again. This picture gives you a better idea of just what I told you. What time do I go to? Okay, about 6:10. Give me a warning. Okay, 7:10. Give me a warning. Okay, this is the same thing, except it's a better, more realistic picture. Actually, they color through it again. If you look at it, you're seeing here's the chromosphere. You're seeing. And if you go, you can go from the core to the radiation zone. Here is a better picture of convection zone that I was talking about. You see, what you're seeing there shows that material gets hot, moved up here, radiates, gets cooled down, go back down, and does it again. Just like the way water boils. And these things that you see, these bubbles that you see on it, those are very important. The surface of the sun is constantly bubbling. If you don't believe it, you know how hot it is today. Okay? But these things are not that little. This one here is about the size of the Earth. So bubbles are not tiny bubbles. Okay? They're big. Now, here I put it here for you to read, and people who are on Zoom, they can read it nicely, so they can see a better idea. That's where the energy is created. Now, let me tell you a tiny bit about the energy part. So, yeah. What happens inside the sun, the way we get the energy, is exactly the same way that we make an atomic bomb, hydrogen bomb. We get hydrogen, we make it very, very hot, and put it under a lot of pressure. They hit each other, get stuck to each other. And once they got to stuck to each other, the constituent, those get stuck together and hydrogen gets converted to helium. And as a result of that, it gives up some energy. Okay, so here's the picture that I want you to see. On this side, deuterium is basically hydrogen atom without a neutron, and a neutron gets attached to it. And sometimes two neutrons gets attached to it, so we call it tritium. And some of you have heard the word heavy water that we need. Heavy water is because they have the deuterium or tritium. That's what they needed for the bombs. So that's what you have. Those get fused. You get a fusion place, and it gets converted to helium atom. Helium atom is very inert until it goes crazy later in this life of the star. And also, you see, if you count, you see that you have 3 neutrons here and 2 protons. The color ones, protons, gray are neutrons. What happens over here, you end up with a 1 helium atom and 1 neutron. But in the process, and that's the important part, you get energy. Okay? And that's the energy you're getting. Now, sun has enough hydrogen to supply us energy for another 4.5 billion years. So we are safe. Okay? And it has been supplying energy for us for the last 4.5 billion years. So is sun giving us energy? And sun is actually not the first generation star. Before the sun and solar system came to being, there was another star that exploded and died and turned into nebula. The nebula gathered itself again and built the solar system. The center of it became a sun and the planets and so on. That's what happened. All right. Now, I'm going to go through this part fast because this tells you exactly everything I told you. And this is in the radius zone. And this is what I was telling you about 170,000 years it takes for a photon to get from the radiation zone all the way to the top.
So it's pretty old. So like.
Yeah. Yeah. It was the light that you're feeling right now that heats your body up was created long, long before you were born. Okay. In fact, long time before our civilization. What do you mean if you know if something happens to it? Well, some of it does get gone, but who cares as long as you get some. Yeah. Okay. Now, I'm going to skip this part. This is the one I want to talk about. That's the craziest part. Remember I told you the crazy part to the sun? This is the crazy part. We have, here's what is happening. Once you get to the surface of the sun and you pass the chromosphere, then sun's atmosphere starts, which we call it corona. This is just a very tenuous gas. The strange things about it is that the temperature of it rises from where it was. You know, remember I told you the surface on the sun was about 10,000 degrees? When you go to corona, as you go up, the temperature goes to about 1 million to 1.5 million degrees as you get further away from the sun. In fact, somebody says if you look at that, it looks like flame is coming out of ice cube. That's how strange it is. And we have been trying to explain how that happens, and we have a very good idea. And I will tell you a little bit about it. But remember, the problem that we have right now, the biggest problem that we want to solve right now is strange things about the corona. One of the problems with it is this. They call it, if you look at the atmosphere of the Earth, pretty much evenly around it. That's not the case with the corona. Some area has A lot of the atmospheres, some areas have none. Okay? And not only that, it doesn't stay constant, it keeps changing. So, and some of the atmosphere turns to tiny streamers. Well, I call it tiny because it goes from here, keeps going. The streamers are somewhere around 2 to 3 Earth long. So sometimes they go even more. Streamers are strange. You and I need to talk about the streamers after one. Okay? Any questions so far? Anybody? Everybody's clear? Cool. Okay, let's keep going then. Yeah.
Can I ask you a question?
Of course.
All right, so you said that the sun is not a first generation star.
Right.
It's the result of products blasted into the nebula. Can you describe to the audience how we know that?
Well, one reason we know is actually the gold that you have on your body. The question was, how do we know the sun is the second generation star? Because the way the stars produce material. You still remember we started with hydrogen? Hydrogen tends to helium, helium eventually tends to lithium and carbon and so on and so forth. Small stars like the sun, they cannot go past iron. Okay, because past iron, you need a different phenomena to produce the elements on the periodic table. So we have the fact that we have gold on Earth. Gold is because another star should have produced it. So gold and heavy uranium, all of those materials that are on the heavy end of the periodic table are evidence that there was another star that exploded whose remnant becomes our solar system. That's a good question. That's good. The stars made the basic ingredients. The answer is yes. But there are some stars, they run out of their hydrogen, like they go through this nova or supernova. And when that happens, they no longer have any hydrogen left. So they're made mainly of helium, and they start burning the helium. Okay, so there are some stars that exploded at one time and turned to like a supernova. Then what they do, actually, their ingredients is not like our sun. It's mainly helium. So, I mean, by far brighter, billions of times brighter, billions of times brighter. Okay, now that brings me to the next one. Again, back to the idea of the dark corona. You see right there, that gas, that piece over here that jets out and comes back down, those are called prominences. And I think those of you who are going to come on 24th to our event, I'm going to show you some real live ones, correct? Yeah, we're going to look at through his telescope. He has a fancy filter that I'm always jealous of. And you can see really cool prominences. And sometimes they break loose. And now these are not small, these are big things. And they shoot the big jet of material from the sun out to the space. And that material becomes what we call solar wind. So that's why we watch for them all the time. Why? Because they disturb our signals on Earth. If Earth did not have the magnetic field around it, it wouldn't exist. But because of these, most of the solar wind gets directed away from the Earth by magnetic field of the Earth. Sometimes actually some of it sips in and comes down and they start glowing. And that's what we call aurora borealis and australis, the two northern and southern light. How many of you have seen that? Cool thing, huh? I am very jealous to see it. I've seen it only in the movies and in the pictures. And my grandson was in Iceland seeing it. That's crazy. Okay, so prominences are sometimes they break out, and when they go up and come back down, they're prominence. And sometimes they break out, we call them flares. So you can see some flares in there too somewhere. You can see the flares happening there too. You see? So But I got a better picture for you today. On the surface of the sun, when the prominences happens and so on, the two footprints that they have, and the reason, by the way, they come about is, remember at the beginning, I told you about the differential rotation. Do you have a question? No. I told you about differential rotation, and I told you the differential rotation causes the magnetic field of the sun scramble. Remember that? And that scrambling is the major problem that happens and causes the explosion of and creating the prominences, things like that. The footprint that remains is, we call them sunspots. Okay, and you can see it, and they're normally come in pairs. Okay, you see the spots? Sometimes we have a lot of sunspots, sometimes they disappear. It's like the pimples on people's faces. Okay, sometimes you get a lot of pimples, sometimes you don't get that many. And that's true with the sun too. Now, except with the sun, sunspots have a period. Okay, at every 11 years to go to a maximum and go to a minimum. Okay, and that is one of the reasons that people are still investigating, don't know, but I'll tell you a little bit about it. Because the magnetic fields that rotate, remember, as differential rotation happens, they need a certain amount of level of density of the magnetic field lines so that they can burst, and that takes time. So actually, there are 3 cycles on it. One is 11 years, one's twice that, which is 22, and one is 44. And that's the very interesting thing. Actually, somebody plotted when I was teaching this about 30 years ago, I remembered it from then. Somebody plotted the rise and fall of the sunspot and plotted it against the length of the skirts of women in the United States, and found out the two correlate with a high correlation. When sunspots were high, the skirts were longer. When sunspots were low, skirts were the reverse.
What are those sunspots right now? Fire.
Ken, they actually are on the high side. Go ahead.
Right now, the sun is headed towards a maximum.
Yeah.
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 So activity is increasing.
And it shows, it's so hot.
Actually, sunspots are cooler. Okay, the reason they call it sunspots and they look darker, because the temperature on the surface, on the greenish yellow part, is about 1,000 to 2,000 degrees higher than inside the sunspot. So when there's a lot of sunspots, temperature go down. And in fact, that's the way we discovered the cycles of the sunspots. When you cut the trees have rings, and the growth of the trees tells you how, depending on the rings that they grow. And from the growth of the ring, when there's a lot of water, the rings grow faster and bigger. But there isn't, they're small. So when you look at it, you'll see on the tree, if you go, for example, Big Basin or some of those, or Yosemite, you can see the cross sections. You can see that period of 11 years is showing up there, because we have the times that we have a lot of water on Earth because temperature is lower, and sometimes we have less because temperature is high.
So are we at like towards the year?
Right now we are at the high. Yeah, we're going to go. We are getting to maximum. We're going to go the other way around, hopefully. Okay, and again, I have this picture to see for you to see that again. These are the bubbling that is happening. If you boiling water on the surface of water, you're going to see something like that boiling all the time, right? You've seen that bubble boil. That's what is happening on the surface of the sun. And except the fact that each one of these is about the size of the Earth. So big bubbles. Okay. Yes. Cool. Very good. Thank you for telling me. When I was going to give this talk, I was in a meeting, I mentioned it to my friends, and they made all kinds of suggestions to me what to do. One of my colleagues Dr. Klomsky, she said, I was just talking to my friend, you wouldn't believe what I saw. I said, what did you see? So you should see this prominence that I saw. I said, send it to me. So she did. And this is what she sent me. Look at that. This is, comes from Minnesota, and this was taken at Minnesota Observatory. This prominence is amazing. Ken, from here to there is 200,000 miles, 25 Earths, okay? If you get 25 Earths, stack them up, you go from here to there. And I thought that is a really, really awesome thing to see. And I needed to give the credit, and there is the credit to the person who did it. So there it is. Okay? I am kind of envious of that one. And it is, I need to talk a little bit eclipse too, because everybody knows that there is a relationship between the moon and the sun and the earth, and then one goes under the shadow of the other. That causes the eclipse. So I need to talk about it a little bit. We ended up, that's a kind of a lucky coincidence. The diameter of the moon is about 400 times smaller than the diameter of the sun. But by coincidence, on the average, the distance from this Earth to the sun is also 400 times more than the distance to the moon. So the disk of the moon, if falls right in front of the sun, it can cause, stops the face of the moon. And I'm showing you here, this is a lunar eclipse, which means that in this picture, you have to pardon, this is my drawing, and that's the best I could do with the word processing. Basically, sun, when rays come here, hits the earth, and then causes the shadow, penumbra, and then moon gets in there. You all have seen the moon turns kind of copper color when it's in eclipse, right? That's what happens. And then on solar eclipse is the one that we want to look at. That's the cool one. What happens when moon gets in front of us? And that's what I was talking about. You see, this distance to there is 400 times more than or the diameter of the moon to the diameter of the sun is same as the distance of the Earth to the moon and distance from the Earth to the sun. Yeah.
Does the moon get like really hot when this happens, or is
Does it get really hot? The moon gets hot all the time. You have to remember, this happens all the time. Only the certain time we end it. Every month it goes through this cycle. But the angle of the orbit of the moon is a little bit tilted, so not always falls in front of the sun. So when it does, you get that effect. But nothing extraordinary happened with that. Now, I want to close my talk with this picture. This is in honor of Ken. Okay, this is the solar eclipse of the 2017. And one thing cool that happens when the eclipse of the sun happens, then we can see the corona. What you're seeing there is the corona. And you see that it's not even, you see how it's streaming all over the place? That is the essence of the corona. And it is cooler here and gets hotter and hotter and hotter as you go out by 1,000,000 degrees. And I recently read an article said that it actually goes up to about 2,000,000 degrees. But I don't know exactly, I didn't see the data. All right, so. Oh, in the one that in the photo you just saw this much. Yeah. But this is millions of miles. This is about up from some areas about 1,000,000 miles, goes up to about 3 or 4 million miles. I'm sorry?
Where did you take this picture? Oh,
Oh. Let him tell.
I took it from Teton National Park. Teton. The Yellowstone is? Yeah. Because that was where the cathode totality. Oh, yeah.
Yeah.
It was a massive pile of people on mountainside. Actually, we were very fortunate in the 2017 eclipse. Almost the entirety of the U.S. Had clear weather all the way from Oregon to South Carolina.
Oh, I had the event being observed on the campus at the Plaza of the Sun. We had somewhere around 2,000-3,000 people there.
Yeah. So anyway,
Yeah.
the only area that were cloudy that day was there were some clouds over Nebraska. Those are the people who would see that much. But from all the way from Oregon through Idaho and Wyoming and it was really quite clear. And then,
Yeah, here in San Mateo, we got a
and then
partial
from
eclipse.
Nebraska all the way down through southern Illinois and into South Carolina, it was very clear. And so there was some patches of clouds in Nebraska, which spoiled their view, but everybody else got a chance to see it.
Okay, with that said, I think that's my last thought. Thank you very much. Sure. I'm ready to answer any questions.
When you refer to the magnetic field,
Yes,
which affects,
the solar wind.
what is that?
Okay.
I mean, I know this is science, but I don't.
Well, if you think about it this way. Think that there is a big, giant magnet bar sitting in the middle of the Earth. That's not true, but imagine that. So magnetic field lines of magnet, if you get the magnet bar and put on iron files, you see the iron files line up from the South Pole to the North Pole, from North Pole to South Pole, depending which way you go. So if you imagine a giant magnet inside the Earth, the magnetic field lines go around and around the Earth. And that's how you have the compass. What creates it actually, because inside, in case of the Earth, at the center of the Earth, the core of the Earth has a lot of metal and they have a lot of free charges. And when the charges move, they create magnetic field. And because the rotation inside the Earth of the core, that creates a lot of the magnetic field. Yes.
What's the status of this exploratory spacecraft that's moving between Mercury and the Sun that has a shield on it? It can do some of the closest examinations of the Sun. I know it's out there. It's heading for, I don't know what you call its closest approach.
Yeah, we're going to eventually sit into
It's going to lose it.
Yeah.
What's the status of that now? Where's it at?
Actually, I don't know. Very recently, we have been so graphite wet that I haven't given up with that. But do you know?
I think there was
The question was that we have a probe that is right now near between Mercury and the Sun.
the Parker probe.
Yeah, yeah.
Parker
Hey,
probe.
the question is, what is the status of it?
It's a spacecraft that's considered to have touched the Sun. Well, can't really touch the Sun, but it.
Eventually, it's going to
spacecraft
melt
that's
into the Sun.
Closest to the surface of the Sun compared to any of the spacecraft that's been.
But to answer your question, remember I told you the corona is very large. And exactly where it stands right now, we really don't know.
Yeah, well, I don't know.
We will know more when it does crash.
So that, when we're looking at that corona
Mhm.
stuff, that happened 170,000 years ago, whatever we're seeing.
The part that you're seeing, the light from it is from 170,000 years ago.
Right.
But what you're seeing, that light that you see gets to us in about 8.5 minutes. Yeah.
So about that thing where it's like 110, that's how long ago that light was made.
Mhm.
So then what's the sun?
What
Are
is-
sunspots also for 170?
No, sunspots are happening not because of that. Sunspots happening because energy is out there already on the surface. And because the sun is churning and turning and turning, doing that, on the surface, the magnetic field gets tangled up.
But the light that we're seeing is from that sun 170 degrees. So what if the sunspots are from 170?
The sunspots come into existence and go away. Okay, think about it this way. If the water is boiling on top of the stove, the reason is boiling because the energy already causes it boil. Where that energy come from, it's going to be long story because somebody in some plant got a coal and turned it to electricity. Electricity came through the wires, came to your stove. That took a long time to get to your stove. But once it is on the stove, it doesn't take it that long to boil the water. See? And that's the same thing happens. The light that was produced in radiation zone, it takes 170,000 years to come up. But once it is there, it can cause the churning of the surface and magnetic fields and produce the sunspots.
I totally get that.
Yeah.
If there's going to be a picture of you or the sun today, the sunspots, and the things that are happening on the sun happened 170,000 years ago, how is it going to seem something that's there?
Well, there are two different things happen. One, like I said, if you think about, think again of my analogy. The energy comes to your stove. You turn on the stove, that energy that is on the stove immediately goes and boils your water. But how long did it take for that energy to get from where it was produced to your stove? That's a long time. Okay, it takes 170,000 years from when it was produced to get to the surface. But what it does on the surface is almost quick. It is a matter of days that it happens. Okay, do you get that now? Okay, good. Anything else? Yes.
Should mention that the next solar eclipse over the US will be 2024.
Oh, that's right. That's right.
So although the path of totality will be from Texas up to Arkansas to southern Illinois, Ohio.
We don't get it here.
And into so if you want to go to the Midwest or take a trip to the Midwest, you can possibly see the solar eclipse in person.
Yeah.
In 2024.
Okay, Ken was saying that the next solar eclipse is going to be in 2024, and if you want to see it, go to Texas. Yes.
You said earlier that for 4.5 billion years, the sun has been making this energy, and it's going to continue to do it for 4.5 more. How can they do that?
Oh, because we know how much energy is coming out of the sun. Okay, and in fact, in your class, you're going to be calculating that. We know how much energy is coming out of the sun every day. I mean, it's not hard to measure, but for example, the heat that you're getting coming from somewhere, we can very easily calculate how much sun puts out energy out. And remember, only a fraction of it comes to Earth. A lot of it goes everywhere else. So because of that, we know at what rate it is burning hydrogen. And we know what the hydrogen supply is, so we know how long it lasts. Yes?
The James Webb Telescope about a billion miles.
Yes.
And it's gold-plated shield that it has. And
Yeah.
whatnot, it's a ray. It's preventing the sun to create interference with the energy of rays.
Well, there's more than one reason. Actually, that's one of the reasons. We want to make sure that the material is inert, okay? And could you please repeat your question louder?
Where is the James Webb Telescope at? How far away from the Earth, and what position was it at?
Okay. The James Webb Telescope is what we call, at the point that we call Lagrange points. One of Lagrange points are the points where if object is there, it can orbit in stable orbit without falling away. There are 5 Lagrange points between the Earth and the sun that produces it. On one of those Lagrange points, we have Park Jim Webb, which is 1 million miles away from here. So centripetal force at that point is just right so that Jim Webb can rotate without losing any energy. Okay, it's a stable orbit. That's why we parked it there. But there's a lot more to it than that, because once we get there, first of all, we have access to a lot bigger universe. There's no interference from the stars, from the twinkling on the atmosphere. All of those goes away. So the other part of it is that, okay, how do we get the energy? Because telescopes work by what we call light gathering. Mike can tell you about that. The more light you can gather, the better image you get. Okay? And that's how telescope works, both refractors and reflectors. Is how much light you get. That's why you see the big telescopes, they make a diameter of the mirror to be about 10 meters because they can gather a lot more light so they can see further. Jim Webb, we cannot make it too big because you have to travel it there. So we have to concentrate that don't lose any light that you catch. That's the key to it. So one of the things that we do, the way we have plated it, is that we lose the least amount of energy. That's why it is the way it is. Yes, anything else? Okay, you have a question on there?
No, people said thank you, it was great.
Okay, thank you. Thank you very much, everybody.